Hello, y'all. Thank you for having me. And today I'm going to be talking about update strategies for edge devices. So this can be a deceptively difficult problem to solve for, especially if you are dealing with a fleet of devices with wildly different capabilities. But there are some tools and design strategies that we can implement that address a number of pain points you might run into. First, a little bit about me. Like you said, my name is Kat, and I'm a developer advocate at JFrog. But before that, I was an engineer at JFrog on the IoT team. And we wanted to bring DevOps to the edge because it should not be as difficult to update these devices anymore. Currently, it's a huge pain. And in pursuit of this goal, we found a lot of interesting solutions that we could bring into a CI/CD pipeline for embedded Linux devices, and eventually built a very flashy proof of concept that put several of these solutions on display. If you want to get a hold of me, you can email me at catc@jfrog.com, but I will warn you, I am not about the whole zero inbox thing. So it might take me a while if you try to email me. Or you can DM me on Twitter at Dixie3Flatline. And if you know what that is a reference to, please DM me because nobody ever gets it. And I'm starting to be concerned that it was too deep cut of a nerd reference. And I'm a little insecure about it. So DM me and I'll send you a t-shirt if you know what it is. I will also have my slides and links to relevant resources and whatnot up at jfrog.com/show-notes after the conference is over. Also, my cat's in my lap. She's really needy and will not make it through this without crying at some point. Just fair warning. So let's get some context first. How large is the edge? If you count both dumb sensor edge devices and smarter ones like gateways, there are an estimated 20.4 billion edge devices today. It seems like a lot, yeah? So how are they being updated now? Some of them can't be. They are throwaway devices, effectively single use. When they break, they need to be replaced. A lot of those that are being updated do it in a way that's kind of unwieldy. It's time consuming, or the infrastructure to support it is complicated, or it can't really happen wirelessly at all and requires physical access, which is either expensive for the manufacturer or irritating for the user. In some cases, it's flat out impossible because the device is so remote. Okay. The way things work now is annoying for users or costs a little bit of money, but the industry is still clearly booming, right? It's 20.4 billion devices. So why should we spend the time and effort to change it? Our lives are increasingly reliant on edge computing and IoT, with devices taking over larger and larger amounts of work in consumer, industrial, retail, and medical spaces. People don't want to spend lengthy amounts of time waiting for a software update to complete, and they definitely don't want to have to plug a device into a computer to do it. Users don't understand that. It's also really dangerous. Infrequent or non-existent software updates, regardless of the reason for it, makes edge devices a pretty serious security vulnerability in anybody's network. Everybody knows that unpatched software is a problem. We all agree on this. This could mean allowing anything from the exposure of user or client data to a malicious third party to devices being harnessed for a botnet or cryptocurrency mining or whatever. This has already happened on a wide scale, and it's continuing to happen today. A couple of years ago, a whole bunch of smart appliances, refrigerators and whatnot got harnessed for a botnet. That seems absurd, and it's honestly kind of comical, but it happens, right? And the safety implications for medical devices are even more extreme. At DEF CON last year, at the in-person one, we were presented with the opportunity to try to attack connected ultrasound machines, and it was actually super easy. Okay, so now we've acknowledged that this is a problem, but what's keeping us from solving it? Just update the thing, right? You kind of can't. A lot of edge devices are simply not designed with the ability to be updated. They expect to run the software version that they ship with until they break. The update strategy for these devices is flashing them. This is dangerous because how often do you write a piece of software with 0 bugs in it? How confident are you in your QA team to catch every conceivable edge case? I know we want to imagine that we're all like ultra efficient, perfect 10x engineers, but we just are not. You shouldn't be that confident because on average, there's between 1 and 25 bugs per 1,000 lines of code. Bugs are making it into production, so you really cannot gamble on your code being perfect. We also can't rely on the device's network. Networks hosting edge devices may be unstable and connections may be intermittent. The speed of the network may be very slow, so we need to keep the updates as small as we possibly can. It probably isn't a secure network either, so these updates need to be signed in some way so that they can be trusted. Those 20.4 billion devices aren't running on any kind of standardized hardware either. Each class of device is running on something specialized with differences in available communication protocols, memory, storage space, architecture, and operating system sophistication. So how do we design a system that takes these differences into account and handles them, allowing for easier deployment to broader classes of devices instead of just a single board or device type? Can we have a one-size-fits-all solution for a market that comes in a lot of different sizes? Probably not, but we can build us something that gets us like maybe one size fits most. First, we have to just stop building devices that can't be updated. Throwaway devices are absolutely not acceptable anymore. Besides the Clarity security problem in having a fleet of devices out there collecting data in the wild that can't be patched if a security flaw is found, the ecological impact of designing single-use electronics that might need to be just thrown away as a result of a bug is completely unacceptable. There are so many of these cheap electronics out there that the 2020 Tokyo Olympics and Paralympics produced all of its 5,000 medals from scraps harvested from discarded electronics donated only by the Japanese citizens. That's absolutely bonkers. It's a huge amount of trash. Design with the philosophy that your product should improve over the course of its usable lifespan. This may not apply to like edge devices that are literally just dumb arrays of sensors passing data along to somewhere else, but it definitely applies to the smarter ones and gateways. The expected lifespan of some edge devices is 5 to 10 years. They should not just be getting worse from the very moment they ship. I'm not saying that you should make sure that it never, ever, ever needs to be replaced, because that doesn't make sense from a business perspective, but give them a couple of years of improvements, you know? Also, a bad update shouldn't brick the device. There needs to be a way to roll back immediately if something goes wrong. I know that sounds obvious, but it happens a lot. Updates should also be trusted. There are a lot of moving parts involved in deploying updates to the edge, and they are easier to manage for a developer if you have a robust CI/CD pipeline in place. It's your developers will thank you. So to drive this point home, we built a proof of concept using the most tangible example of an edge device we could think of, a car. Not a real car, though. Obviously, JFrog wouldn't buy us one to potentially brick, which is Kind of a killjoy, but totally fair IMO. So we had to build our own. We used a Raspberry Pi 3B Plus strapped to a remote-controlled car. An Intel NUC is sitting under the driver's seat that you see here, passing commands from the Logitech race wheel to the Pi on the car. People could interact with this proof of concept in one of two ways. By driving it, as you can see in this picture, that's our ops guy, Frankie, or as a developer pushing code updates to the car while someone else drive it. We actually allowed real randos to write and deploy code to the car, people we did not know off the conference floor. That's how confident we were in the tools we used. The car was also capable of driving itself using a heavily modified version of the Donkey library, and the driver could choose to record their laps to retrain the existing driving model if they wanted to. So let's talk about cars now. The overwhelming majority of cars cannot receive software updates over the air. I know somebody is thinking, oh, my Tesla. Yes, your Tesla. Your Tesla can. Your Tesla is the exception, not the rule. Most cars really cannot do this, which sucks because there are a lot of computers in your car, like at least 4 in modern ones. They instead need to be brought into a service center for it. And those updates can take hours. Cars that can be updated over the air still take a while to do it. Again, Tesla is probably still the best at this, but it isn't immediate, and the car can't be driven while that's going on. Different cars are also using different boards and running on different operating systems. So even within one corner of the market, there is no real standardization yet. Personally, I hope we standardize on automotive grade Linux, but we'll see how that goes. Also, 15% of vehicle recalls are a result of bad software that needs to be updated. For example, Jaguar had to issue a recall a couple years ago to fix a problem with the brakes. There was an issue with the computer running the brakes that caused a regenerative braking system failure, and that was a bug. It was a software problem, but they couldn't update over the air, so they had to issue a recall. Another car stranded its owner in the car on the highway for hours because it could do over-the-air updates, but it couldn't roll back a bad one. So this is a very real, very painful, and very potentially dangerous issue that presented a range of solvable pain points for both the end user and the manufacturer. The combination of all of those issues into one single device made it a great example for proving that we do not have to do things this way anymore. There's a better way. Because we were working with a car, we were very motivated to make this update happen quickly, reliably, and without the potential for injury to the user, because in this case, the potential for injury to the user means potentially killing the user. So we had 2 distinct workflows showing off 2 distinct strategies for this proof of concept. For one workflow, we updated software running on the car without flashing its firmware. It's very quick, about 35 seconds, doesn't interrupt the user, and supports rollback. This workflow relied on K3S and Helm. For the other, we updated the firmware itself in just a few minutes with the ability to automatically roll back again if a fault is detected. This one relied on Mender, Yocto, and Artifactory. All updates are scanned for vulnerabilities, and everything is triggered automatically through a CI pipeline. So let's look at the software workflow first. This is a quick overview of the technologies at play in a workflow for the software updates on the device, just an application. We used JFrog Artifactory to manage and store all of our various build artifacts. There were a lot of them, as well as handle promoting builds from development to production. X-ray is used to scan for any vulnerabilities, anything known. Oh, sorry. And we've got K3S and Helm used to deploy to the car. Since it already integrates with Artifactory, we used pipelines for our CI tool here, but you could use whatever. Let's look at these tools in a little bit more detail. So if you aren't familiar with Artifactory, it's a universal binary repository manager, and we had things from a lot of different sources involved here, so we needed something that was a little more broad. It supports a ton of packages right out of the box: Maven, PyPy, NPM, Go, whatever. This project was mostly Python and Go, but we had pieces coming in from so many different places. It was outrageous. Plus, it has a generic repository type, which I will talk about later because it actually did a lot of work for us. You can also use it as a private Docker or Helm registry, which was important too. It does a lot of really heavy lifting for this demo since it's managing 1,000 sources. Next up is K3S, Kubernetes, but 5 less, the absolute cutest slogan in open source. I love it. K3S is lightweight Kubernetes designed for edge devices. It uses only 512 megabytes of RAM, produces a binary of just 40 megabytes, and has very minimal OS requirements. The packages required dependencies are just containerd, Flannel, Core DNS, CNI, and some utilities like IP tables and SOCAT. It is wrapped in a launcher that abstracts away some of the complex issues like generating TLS certificates and whatnot for secure communications, and sets a few options for you by default. This was actually my first exposure to Kubernetes as well, which may be like terrifying to some, I guess. It was definitely like being thrown directly into the fire for me, having to learn Kubernetes under such an extreme constraint as getting it to run on a Raspberry Pi, but you know, whatever. If you use Kubernetes, you might already be familiar with Helm, the package manager for Kubernetes. Still, I'm going to go over it a bit because I doubt everyone watching this knows what it is. So Helm uses charts to describe complex applications and allows for an easily repeatable and predictable installation. Your charts serve as the final authority on what your application looks like, and they are also pretty easy to version, and they support quick rollbacks if something goes wrong. So all good. This is part of one of the Helm charts for this demo. It's just building a microservice we were using to allow us to control the miniature car with the racing wheel from the image in an earlier slide. The syntax here is fairly simple. It's just more YAML like the rest of DevOps, much to my dismay. So the result is that using these tools made updates to the applications running on the car fairly quick and efficient. It actually was not a huge amount of effort to build this out. The average amount of time from a developer pushing an update to deployment on the car was about 35 seconds, with 0 interruption to the user at all. It can happen while a device is in use. I don't think that that means it necessarily should happen while the device is in use, while the car is being driven. For most updates, there should be consent from the user involved, or we should at least like tell them it's happened. But designing your edge device with this strategy in mind does mean you can update silently. So for edge devices without any user interaction and no need for a full firmware update, this is a pretty compelling option. Let's talk about the firmware workflow. So similar to the software workflow, this is an overview of what would happen in the firmware update. We have Yocto being used to create our builds. We have pipelines handling all of the events again, and X-ray making sure we're not pushing any known serious vulnerabilities again. We used that so heavily mainly because we were like super concerned about somebody off of the conference floor being malicious and trying to like actively damage the demo. So we went a little bit overboard on security and sanity checks for this. We're also using Artifactory again, but this time for more than just storing binaries. It is handling some of the workload for Yocto for us, storing its build cache to make things faster later on. We also have Mender. It's being used to handle our over-the-air deployment in this case. So let's see. Let's talk about Mender first. So Mender is really cool. It's just over-the-air updates for embedded Linux devices, and it's a pretty powerful tool. It ticks several of the boxes we're looking for here. All of our updates are cryptographically signed and verified. It supports automatic rollbacks to a previous build if a failure occurs, just like we need. It also offers several installation strategies, but we're going to focus on the dual A/B strategy. Using this method, two partitions exist on the device, A and B. Duh. The bootloader is aware of which partition is currently designated active and which is not. During an update, the new firmware is streamed directly to the inactive partition. At this point, the partition running the update is designated active, and on reboot, the bootloader will start that partition instead. But because the partition running the older software still exists, although it's designated as inactive, Mender gives us an additional layer of security, local rollback. If there's an issue with a new build that wasn't caught in earlier testing that prevents it from booting correctly or whatever, Mender can automatically just roll back to the previous version by switching to the inactive partition. The use of Mender's dual A/B strategy alone adds a lot of additional speed and security to your deployments, but we still haven't really addressed the issue of the size of our builds. Enter the Yocto project, providing custom Linux distributions for any hardware architecture. Yocto drastically reduces the resources used on the board and minimizes your hardware requirements by allowing you to build a custom Linux distribution without certain modules that are unnecessary for your particular hardware or for your particular project. So say you know that your thing is only going to need to communicate over Wi-Fi, but your board does support Bluetooth, you can use Yocto to build something that doesn't come with the ability to communicate over Bluetooth at all. Like the operating system just lacks that module. You can also build one that doesn't have the ability to communicate over Ethernet, and on and on and on. Bitbake is the syntax used to write recipes for the build, which I think is super cute, pulling in layers like a cake for different hardware configurations and applications. So we used a layer for the board itself, the Raspberry Pi 3B Plus, as well as layers for K3S and Mender. Yocto already provides like a ton of hardware layers for common configurations to get you started really quickly, but custom layers can also be written to isolate specific applications or behaviors. As an example, this is part of the meta layer that adds K3S to our Yocto build. Bitbake syntax is pretty straightforward. It allows for execution of both Python and shell scripts in parallel. You don't need to be like a great engineer to use Bitbake. It's fairly, I'm not going to call it easy because I don't like that word, but it is fairly quick to pick up. So the first build will take a while, but we can speed things up pretty drastically for future builds. Yocto caches everything it downloads during a build, which allows for incremental updates. If you haven't used this build cache, it will only rebuild what has changed. So this is where Artifactory becomes useful again. We can use a generic repository to store the Yocto build cache and tell Yocto to pull from that during subsequent builds. This reduced the time required to build for us by as much as 50%, which is a pretty significant difference. So the result here is that using Mender to handle the deployments and our local rollbacks, and Yocto for our builds, when we're pulling the build cache from Artifactory, the time for a full firmware update was between 5 and 10 minutes after the first build. The build's as small as possible, minimizing potential issues with low bandwidth on the device's network. Updates are signed, satisfying the security requirement, and automatic rollbacks are in place in case of a failure. So we succeeded. It's so fast that, for instance, you get in your car to go to the grocery store, and your car needs an update. Yay. While you're driving to the grocery store, it streams in the background to the inactive partition. You get to the grocery store, you park, you turn your car off, you go in, you do your shopping. You come back out, you turn your car on, and the partition flips, and the updates occurred, and it hasn't interrupted you at all. You didn't even have to do anything other than acknowledge that you want this. Better than the way it's happening now, IMO. Let's recap. So the way a lot of edge and IoT devices are being updated now, if at all, is broken. It is a gigantic security flaw that really needs to be addressed. And it does not have to be this way. We have technology available now that handles some of these problems. I know that we solved it for one device and it was a proof of concept, so some things were different, but it was a proof of the concept. It can be done. For edge devices running embedded Linux, which is what that Raspberry Pi was, a modern DevOps pipeline and a handful of open source tools makes it almost as easy to deploy updates and security patches to an edge device as it is to any other application. There's just some additional infrastructure involved. Thank you for taking the time to listen to me today. I hope I brought you some useful information or at least an interesting perspective. If you have questions, I will take them soon, or you can DM me on Twitter. I will also be putting this slide deck and links to all the resources I mentioned during my talk up at jfrog.com/show notes after the conference is over for you to go through at your own pace. If you like DevOps and you like party games and you like watching alleged DevOps thought leaders embarrass themselves to entertain you, then you might be interested in attending DevOps party games tonight, or at least watching it on Twitch. You can go to DevOpsPartyGames.com for more information on who's playing tonight. It's a lot of actually famous people, not hacks like me. So, what questions do you have for me?
All right, Kat, thank you so much. Let's kick off the Q&A. So we're talking a little bit about security and IoT, and even reference some interesting attacks that leverage botnets and those IoT devices. And some of those devices can't easily be patched. So what should we do to bake in updatability into our devices before we ship them?
I mentioned a few of these tools in my talk, but I think probably the most important for at least embedded Linux devices is K3s, just to make it like easier and faster to just like blast out a new update. That did a ton of the heavy lifting for us on the small updates. It really was most of the work.
Cool. Okay. And then I guess another question would be, does updatability at the edge pose any additional concerns for security at the edge?
Mixed bag. Yes, it can make some security issues a larger problem. Obviously, the additional ability to communicate with the device introduces an attack surface, but we ultimately decided with the rest of software that being able to update more frequently was a good thing for security, because if a flaw is found, if something is exploited, then we can just roll back faster or push a patch faster, a fix. So yes, in some ways it does increase the attack surface, but if you build out a system like this, it's so much easier and faster to push an update that I think the risk is worth it, and that ultimately it results in a lower attack surface.
Okay, great. So that wraps up our short Q&A here. We will have a more extended breakout after lunch. So come on, hop in, continue that conversation.